All right. Last topic here for this section. This is a very long section of notes. And so in this unit, you don't actually have many sections. And so just to kind of go over things, like you really need to be good at dot structures and you really need to be able to navigate those, because other topics like polarity, again, go back to that ability to draw a dot structure. And so when we talk about polarity, the things that we're going to look at are based upon that dot structure. So what is a polar molecule? What is a non-polar molecule? So first we got to understand what we're talking about when we're talking about polarity. We're talking about a molecule that basically is not symmetrical. A polar molecule is not symmetrical. And so we can just write down a definition for polar is that this is a non-symmetrical molecule. So if you don't know what symmetrical means, it just means that something is the same on all sides. So non-symmetrical means that it has ends. So it has a distinct parts of the molecule are going to look different. And this is because it's non-symmetrical, or it has a non-symmetrical distribution of electrons. And so what does that mean? That means that the electrons are sliding to one side of the molecule or another. And so what that means is that one side becomes positive and one side becomes negative. So if we kind of look down here, we can look at this water molecule. So this water molecule has some lone pairs up at the top. So what it does is that it makes a bent shape. And that bent shape has electrons at the top that push the hydrogens down at the bottom, so it doesn't look the same from all angles. And so what happens is that the spot where those electrons are hanging out, it's going to become a little bit more negative. And so the top of the molecule is a little more negative and the bottom is a little more positive. And so then you get this plus minus situation working, which is where you get the concept of the poles. So the poles are, like, if you think about a battery. So here's a battery. If you look at a battery, it's going to have a plus end and a minus end. Well, that's the same thing with the molecule. This water has a plus end and a minus end. So like when a water, it orients itself with another water, they're going to line up. So like with the oxygen, it's the negative side. Then if another water is going to align itself, then it's going to align itself down here like this, because this is a positive end and that's their negative end. And so then you kind of see the way the water molecules will attract to each other, like in water, ice, etc. So you've got to be able to figure out polar or non-polar, and I'm going to give you guys some tricks for that. So let's go back to non-polar real quick. So obviously if you have non-symmetrical, then polar is just going to be the opposite. So polar is just going to be, probably go back to red. Polar is just going to be symmetrical. So it's going to look the same from all sides. And so when we look at these molecules, there are some clues that we can use, but we do have to kind of understand the shape, because the shape is going to tie into this idea of symmetry. So let's go look over back here. We used this program before. So actually, let's just look at this. Here's methane. Now look at methane. That's an AX4E0. It is 100% symmetrical. Everything looks the same from all angles. That is not polar. So then let's go look at something else like the water. Now look at the water. The top has the electrons, or I can make it the bottom. But see, there are different sides. And so down here, where these lone pairs are at, that's going to be the negative side. And then down here, where the H's are at, that's going to be the positive side. But this is not the same from all angles. And then we can go ahead and look at another one. But look at this one. This is square planar. So square planar, if you sit it like this, it is now symmetrical, right? Like it looks identical from all angles if you kind of sit it flat, or you can kind of twist it like that. The electrons are going to space themselves out. So square planar is one of those ones that's going to be a bit of a trick for us. Another one that becomes a trick for us is this linear one, this AX2E3, because it is not polar. Because if you look, it is symmetrical. They're able to create something that, if you look at it, it is evenly distributed. And so those are kind of the weird ones. Now the easy ones are like that. Well, that obviously has a top and a bottom. So anyway, idea of symmetry. So there are a couple of easy ways for you to remember this. So let's go up here to polar, and you're going to want to know these. These are going to be something that'll be on the test. And so here's two ways that you can become polar. So if you look at a molecule and you get a yes for this or a yes for this, it's polar. If you get two no's, it's going to be not polar. Okay, so the attached atoms are different. So what I mean is that the X's are not the same. Okay, so if you look at this one, here's our central atom, carbon. It has an H on one end and an N on the other. So that means it doesn't look the same from all angles, so it's automatically polar. So what happens is that with these electrons, the nitrogen is actually going to pull the electrons over to its side. So the nitrogen side is going to be negative, and then the hydrogen side is positive. So kind of like our battery, that's what's going to happen. You don't need to know what happens. You just need to be able to look at this and say, okay, I have an H on one side and N on the other. They're not the same. They're going to play tug of war with those electrons, and those electrons are going to slide to one side or the other. The nitrogen is going to end up winning that tug of war, right? So that's the first way, the easy way, just to kind of look at your molecule, and if the X's are not all the same, automatically going to be polar. Here's the one that's a little more tricky. If there's lone pairs on the central atom, then it's going to usually be polar, okay? So if you see dots in the middle, it's going to be polar, but there are exceptions. So probably need to write those down. And this is the main way we figure out polarity, is the lone pairs. But the two exceptions are the the square planar and the linear. So let's just go ahead and write that here. So except, so this is kind of like a everything but, except AX2E3. So what happens is that those lone pairs cancel each other out. And we were looking at that over here. There's that AX2E3. So what happens, see those lone pairs, they actually can move and find an even distribution, which creates a symmetrical molecule. And then square planar right here, which is going to be your AX4E2. Those are ones that can get us into trouble. So I'm going to put those down here because we really need to be careful. So that's AX4E2. These are the exceptions. So everything else with the lone pairs is going to slide into the polar category. So we can look at this one here. CH3Cl. So we got a C in the middle, but look, these are all H's. but that's a Cl. So it has different X's. The X's are not the same. So like if this was an H up here, it would be not polar. But since it has H's and then a chlorine around the middle, the chlorine actually pulls all the electrons to its side. So this ends up becoming polar, right? So the tug of war is actually won by something. The chlorine wins, and so it pulls the electrons to its side. Here's NH3. It has lone pairs at the top, so it's polar. We talked about the water. And then here's some nonpolar examples. See right here, the fluorines, they're all the same. There's no lone pairs in the middle, so it's not polar. Carbon tetrachloride, same thing. All of these are the same element, and there's no lone pairs in the middle, so not polar. All right. Now, always polar, usually polar, varies. Basically, you got to be kind of careful with terms like always and this chart here is useful, except for this word right here, usually nonpolar, because you always have to check the elements. Okay, so what's always going to work out? What's always going to be polar? Well, bent, both of them. So both of your bent molecules, they're obviously not symmetrical. The pyramidal, so that's like the one I showed you a minute ago. I showed you a pyramid. The T-shape, obviously T-shaped looks different on one end than the other. The seesaw, remember it's not a teeter-totter. The old seesaw. Square pyramidal. It has the square on top, but there's nothing on bottom, so it looks different on one side than the other. And then the ones that vary that you got to be really careful at are linear, because you have to be careful of linear. You just kind of have to look at it, but you got to be really careful with linear. And then the usually nonpolar, we got to be careful with that word usually, because if there's different elements around the central atom, it can change. But the usually nonpolar are going to be the other shapes. All right, so you just got to be really careful with the usually nonpolar. These over here, these are guarantees. Okay, so what I would remember is how to do it, which is right here. I would remember these two items. Are the atoms around the outside different? And then, do I have lone pairs? Those are the ways that I would focus in on polarity. My time there, I'm going to run out of time on this one. We're going to go ahead and do this right here. So I would have you pause the video, or it's going to stop because this is the end of this one. Go ahead and try this for yourself.